okay, this session is being recorded and it'll be posted in the recorded presentations page. So here's what's on tap for today and for the rest of the semester. Today I'm going to cover modules 14 through 16. We're going to look at the theory and operation, kind of a 60,000 feet level of how routing works, both static and dynamic routing. And then in the last two chapters, we'll cover actual static routing commands, which is an objective for this particular CCNA3, switching, routing, and wireless essentials. And then when we come back after spring break, we'll go right into a dynamic routing protocol, which the only dynamic routing protocol in CCNA is OSPF, Open Shortest Path First. Thursday, we have an in-person lab opportunity for the Static Routing Lab 15.6.2. You can come in person, you can do it remotely using Packet Tracer, that's your choice. Next Tuesday is personal work day. There will be no more recorded or live sessions after the Thursday lab session and today's lecture session. The written final exam, which together with the 5 exams on the Cisco Networking Academy website, netacad.com, all adding up together, average to 50% of your grade. The other 50% of your grade comes from the labs. I do drop the lowest lab grade so you can safely miss one lab and it won't hurt your grade any. So I will turn on the practice, I will turn on the real final exam, which normally you would come for an hour. During normal times, you would come for an hour in person and take it. But what the administration has asked us to do for this time is turn it on for a whole week. You only take it once. You still only get about an hour to take it, but you can take it anytime you want from 9 a.m. Tomorrow at 9 a.m. through a week from tomorrow at 9 a.m. Wednesday, March the 3rd through Wednesday, March the 10th from 9 a.m. That whole week period, that whole 7-day calendar period, you can take that exam from any time during that point. Now, I didn't make it very clear here. My fault entirely, I'm so sorry. Before Cisco Networking Academy website has a business rule, sometimes in business we call this a business requirement, that before you can click onto the final exam and take it, it's just like the chapter exams, the module exams. It's fill in, click and choose the one or the correct two, whatever they tell you. Before you can take that exam, you must take it's a student satisfaction survey. It's called the course feedback form. Now they're changing the name in some of the other courses, but it's still called the feedback form now. Take the course feedback form on the Networking Academy site, and you have to take that before you take the final exam. If you try to take the final exam and you have not yet taken it, it will tell you have to take it first. It's a totally anonymous, completely anonymous satisfaction survey. And I can't see anybody's individual results or anything like that. You have to take it. If you want to take the final exam, you have to take it. Now, we have a similar student satisfaction survey on Web Advisor. It's in the left-hand column under course evaluation. That's a similar anonymous survey. Nobody can see, no instructors can see any individual student, personalized way identifying what any individual student says. Furthermore, the instructors can't see it until after all the grades are turned in. So there's no way it can affect your grade. Final deadline for all work will be a week from 9 a.m. tomorrow, Wednesday, March the 10th. All work must be turned in by that point because the dean is mean and I got to turn it into him or he'll get mad at me. Okay, so we're recording. Good deal. All right, now we're going to go ahead and start talking about the theory and concept of routing. This is layer 3 function. Routers have a function of choosing the best path. So what happens is, when a router receives a packet, he's going to look at that network that's in the destination. Packets, IP packets, layer 3 packets, doesn't matter whether IP version 4 or IP version 6. They have a destination IP address, of which, like a telephone company, telephone number, first part's the area code, second part's that individual number. In IP network addresses, the first part is the network identity, and the second part is the individual host machine on that network. We just care about the network prefix. So when a router receives a destination network, he sees it in a packet, he's going to apply the network, the subnet mask, and he's going to isolate the network address. And then he's going to look in his routing table to see what he should do with that particular network address. This is the routing function. So what a router does is first of all, when he receives the packet, he looks in his routing table. And according to the information that's in that routing table, he will make up his mind that, oh, it is actually possible for me to forward this packet, and I'm going to forward out one of my other interfaces. The information on the routing table is going to tell him this information. It's possible in some circumstances that he doesn't know what to forward it to and have to drop it. But we'll talk about static default routing, which usually takes care of that stuff. So the router looks in, he looks in this routing table. So we have a routing table that's got some entries in it, and it has static route. Well, we haven't even done the code for static routing yet. We've just looked at the router's routing table and seen the directly connected entries. So router R1 has got a directly connected network on the left, and he's got a directly connected network on the right, which is he's relaying information back to the home office. And someone has placed a static route on this network because the router has no directly connected networks for the .3 network. He doesn't know how to get there. Unless we place that static route on this router, he would drop any packets that were addressed to 192.168.3. something, because he wouldn't know how to get there. But someone has gone into this router R1 and created the static route. And now R1 knows that to get to 192.168.3, he needs to send it to the next hop address of 192.168.2.2, which is this port right here. And he'll send it there. So he determined the best path, and he forwarded the packet. In this case, he forwards it out. That jagged red lightning bolt connection in this graphic represents a serial connection, like the old dial-up T1 lines or data lines you would go between one office and another office. Okay, which one is the best path? What if there's more than one way to get to this destination network? So the longest match, which is the longest number of binary bits that match in the prefix, will always be the best choice. If there's more than one way to get there, and there's one line in the routing table that just 16 bits of it match, and there's another line in the routing table that 24 bits of it match, he will use the longer match, the 24-bit match one. So this is sometimes called the prefix length. Prefix length refers to both IP version 4 and IP version 6 addresses. So here's an example of the destination network addresses 172.16.0.10, and this address has been reduced to binary. Now the network portion of this address is this first 26 bits. So looking in his routing table, if he's got one routing table entry that only has 12 bits that match, and he's got a second routing table entry that has 18 bits that match, and he's got a third routing table entry that's got 26 bits that match, the longest match, the 26-bit match, is the most desirable one to use. So in this case, there was ambiguous information. He had 3 different entries. He's going to choose the one that's the best match, the longest match. And he's going to use whatever directions were in the routing table entry for that one. Send it out to that next hop IP address, or send it out that egress interface, exit interface, so it can get there. Now in IP version 6 land, it's the same way. If there's a routing table that only 40 bits match, well, that's somewhat of a match. If that was the only one I had, I would use that. But look, there's a second entry that has 48 bits that match. Well, that's more desirable than the first run. And in that case, the third entry doesn't match because it doesn't match the numbers exactly. So he'll use the second match. It's the best match. Now, how does the routing table get built? Now, we didn't have to do any routing statements whatsoever to get our directly connected networks into the router. Automatically, when a router has, say, 2 Ethernet ports attached to him, and you apply an IP address to your Ethernet ports and you type the no shutdown command, and there's a wire plugged into the Ethernet port so the link light can come on and physically it can come up and up, then that local interface is automatically appears in the routing table. It's a directly connected network. It's the router's own network, so he knows it's there. And he automatically puts that C prefix, directly connected, into the routing table, and you can route back and forth between your 2 Ethernet ports without having to do any routing commands whatsoever. Now, networks that are not directly attached to router, say our router R1, he had 2 directly connected networks, the 1 and the 2 network. There's 2 ways that they can learn about route 1 networks. Now, we're going to take a look in the next chapter about using static routes. And then after we see it's a little bit cumbersome to type in static routes and they don't adapt to changes, they're good for security and things of that nature. But most of the people would use a dynamic routing protocol. It's like we're going to study this after the spring break. We're going to look at the OSPF dynamic routing protocol, which automatically adapts to changes in the network. He tries to heal himself and keep things working properly. So since static routes are kind of a pain to use, in most companies, we're going to use some type of dynamic routing protocol within our corporation. Here's the big picture for today, you guys. This is the big picture. we're going to use a dynamic routing protocol within our company, like OSPF or EIGRP or RIP, to provide connectivity within our company. But we still need connectivity to the home office or to our internet service provider and the 750,000 routes that are on the internet. And we're going to put in a static default route to point to our ISP's lease line so that we can get access to their $1 million Cisco 7500 router, which has all those routes in it for us. We're going to specify a default route to do this. So if I fail to specify a default route and someone types into their computer some address, some location that's not within the company, the router will drop it because he doesn't know how to get there. But we're going to specify a default route on our router that's connected to the internet, our internet service provider, and then we're going to distribute that route, redistribute that static route, default route to all our other routers in the company. And that way, since the default route has a 0 prefix length, that means no bits need to match. So when you do show IP route on a Cisco router, he calls this the gateway of last resort. So it's pretty easy to configure this default route. We're going to enter the command IP route 00000000, and then point to our interface that actually connects to the lease line that goes to our internet service provider. We'll get more of that in the next chapter. Now let's look at this packet forwarding feature. So a packet arrives, number one, the packet arrives at the router. Now it's encapsulated in a data link frame like Ethernet. So the orange parts here are the Ethernet header, which has the Ethernet source and destination address, the Ethernet trailer, which is the frame check sequence of the CRC, so we can make sure the Ethernet frame's not bad. And encapsulated within an Ethernet frame is a pure IP packet. It can be IP4, IP version 6. And so the router is going to look at that. First of all, he's going to check and make sure the Ethernet frame is okay. The data link trailer, CRC, frame check sequence doesn't have any errors in it. He's going to accept the Ethernet frame and not discard it. And he's going to open up that frame and pull out the blue part, the IP packet. And then he's going to look in his routing table, and he's going to look at all the entries that are in the routing table. And if there's more than one that match, he'll choose the one with the longest prefix length, the longest, most number of bits that match, just like we talked about. Find the longest match, number 3. Now, if there are no entries that contain any matches for this, he throws away the packet into that's the bit bucket. That's the trash. It's not going to be forwarded because he doesn't know how to get there. But let's say that one of them does match. So if it's a directly connected network, has that C prefix, he's going to take that destination packet and he's going to re-encapsulate it in another Ethernet frame, and he's going to send it out his directly connected interface to the other device that's on one of these devices is directly connected to this router. This router is a default gateway. If it's on another network, he's going to forward it to another router. This means it's not a C, it's not a directly connected prefix. Either he will learn from some dynamic routing protocol like OSPF, or there'll be a default route established that'll say, forward this packet to that router that we have that connects to the ISP. And he will look in his routing table, and he will look at that information and forward it for us. So it could do one of these two things. It could forward the packet to a device on the directly connected network. Now, if he's forwarding it to another device that's on the same network as you are on, he's simply going to put it in another Ethernet frame and forward it to the other device. Now, he might need to do an ARP request and ask that forwarding device that being forwarded to what its MAC address is. And it could be an ARP request if it's IP version 4, or a neighbor determination request if it's IP version 6. Same mechanism. Says, I know your IP address, tell me what your MAC address is, I've got something to send to you. I got to put an Ethernet frame, I have to know your MAC address to do this. Now, if it's not a directly connected network, I might need to forward it to another router. Keeping in mind there's typically 10 or 15 routers between you and the website you're connected to. He would look at that information on the routing table, and it might have an XOP IP address, or it might have an exit interface like G00, and it would say, send it out there. Now, if there is no best path, the packet could be dropped. If we haven't established a default route, a default static route, it would be dropped because it would only match things in our internal company network. So the forwarding of information. I'm going to take this layer 3 packet and I'm going to encapsulate it in some sort of layer 2 technology like an Ethernet frame. Now, it could be, we don't have much stuff about serial links anymore. Serial links are not very popular anymore, like the old T1 lines would come in through a serial link. But most of the time these days, we get some sort of Ethernet handoff, like your home DSL cable or cable modem has an Ethernet plug that plugs into your home router. But these technologies do still exist, and if it's a serial port, we have to choose the right type of serial port protocol. And Cisco routers have a default serial encapsulation type of HDLC. Point-to-point protocol is an open standard that the Hayes dial-up modems use. Everybody understands that. Could be some other layer 2 protocol. Try not to worry about this. Okay, there are 3 different methods by which the Cisco router can do this process of picking up the packet and forwarding it out the appropriate interface. And let's look at these 3 different methods here. And just to give you a sneak preview, process switching is the slowest, fast switching is faster, and Cisco Express forwarding is the quickest, but it requires expensive silicon to do this. So in the process switching mechanism, the packet is going to come into the router, and it's going to look at the routing table, and the routing table is going to say forward it to the, he calls it the egress interface in this diagram. That's the X interface. That's the interface that's been chosen to forward it, the best path to forward it to, so it can get to the next relay point to get to its destination. So this process takes a lot of the CPU power of the router. Every individual packet has got to be individually studied and determined what exit interface to send it to. So if we can use a faster method, it's better. Sometimes when we do things like turn on some type of process like debugging or other processes, it may slow it down and have to use this procedure. Okay, fast switching is we're going to take a copy of the routing table and we're going to put a copy of it, it's called a cache, in some fast silicon. And we're going to have to look up the first one. Yeah, we're going to have to look up the exit interface on the first one. So the idea is if I'm sending 1,000 pages to the printer, I don't want to have him look it up 1,000 times. He's going to look up the first time, and then the other 999 pages to the printer will zip real fast to the destination port and give us better performance in the router. Now, the best method is if I have got our little routers don't have this function. But if we have a more expensive router that's got some dedicated silicon, you know, something that's at the core distribution level or an ISP, they need fast performance because they have millions of customers. What we're going to do is take a copy of the routing table from the CPU, and we're going to create something called the forwarding information base. And we're going to put it in the silicon. Silicon is faster than software. And every single, even the first lookup in this case, will be done by the forwarding information base. The more expensive routers use this method. Now, if a software problem occurs and the CPU crashes, it keeps forwarding data. The forwarding information base has been loaded into the silicon. It's not crashed, it's still running. This is the most desirable technique, particularly when you got lots of heavy traffic and you're someone, like an internet service provider where you have lots of packets that you need to forward very quickly. So let's look at the configuration of the router. We're going to use this topology here and look at R1. And R1 has got a gigabit port going to the upstairs lab, and it's got a gigabit port going to the downstairs lab, and then it's got a point-to-point connection back to the home office. And we've seen most of this configuration type before. We're going to go into the privilege exec mode and go in the configuration terminal mode. Prompt changes to router config. We're going to give it a host name. We're going to put in the enable class. We're going to put in passwords. We're going to put in the appropriate passwords for the console port and for the VTY virtual terminal ports. We're going to do service password encryption so that all the passwords, these passwords here, will not be shown in plain text form when you show run. We'll put a nasty gram on the screen that our lawyers told us to say. And then he's going to go through and add IP addresses. So he's going to adding his IP version 4 addresses and his IP version 6 addresses to this gigabit 00 port. He's adding hv 4 and IPv6 addresses to the gigabit 001 port. And he's going to that serial port, which is a link to the other router across the phone line, probably in another location, physical location. We had to lease a data line to go to that location. and he's getting his IP version 4 and IPv6 addresses. And of course, he has to type no shutdown, because on a router, the ports are shut down by default. You have to type no shutdown to bring them up. And then he saves the configuration by typing copy run start to the NVRAM. So commands we can check this out with is we can type my favorite command, show IP interface brief, which you can abbreviate SH, IP, INT, B, or SHIB for short. And it very quickly tells you, is the interface up and down? What IP address has been assigned to it? I could type show running configuration and zoom in on the interface and look at it instead of looking at all 3 pages. I could type show interfaces and show IP interfaces to see that. And you can also type show IP route and see what's been installed in the routing table. So anytime you have a serial or Ethernet interface on your router and you brought it up and put an IP address on it, it's going to appear as a directly connected network in the routing table, so you can see it there as well. And then we can use ping to make sure we have IP connectivity and our wires are plugged in properly. Almost all commands that show IP something, if I want to see, if I'm running IPv6, I can choose show IPv6 and see the IPv6 equivalent of that command. There is a feature in the show run that you can type show, and I don't want to look at all 3 or 4 pages and then look for what I'm looking for. I can show section and show an entire section. I can show include and just jump right to, say I want to just look at the VTY lines. I could do show run, include VTY. I could even use exclude and knock out something. Or I can do show run and begin with a certain line and see everything beginning with there. I can use that with any show command. Now let's look at our routing table. We have directly connected networks, which are the ones that appear with the C prefix, and also there's an L prefix. In the newer routers, version 15.0 and above, version 12.x iOS and previous just have the C. But since 15.0, which has been out for about 10 years now, they also show you, I call this it's kind of like the link local address. It shows you the actual complete 32-bit IP address of that interface. So it's another way you can see it just looking in the routing table. If it's a static route, it'll have the S prefix. That means someone has typed the command IP route and they put in a static route, which we're going to see the syntax for that in the next chapter. If it's a dynamic routing protocol, there'll be a letter corresponding to this. Now, the only dynamic routing protocol that's in CCNA is OSPF. But there are other routing protocols that companies may be using, like EIGRP or RIP. If it says S star, that means it's the default route, the gateway of last resort. That is the routing table entry that points back to the home office, or in a case of a single office, points back to the internet service provider so that they can get to destination places that are actually on the internet. So here's the Zen of routing. Principle 1, every router makes his decision alone based upon the information he has in his own routing table. He doesn't know what's in the routing table of R2. Now, R2 may have told him about a route, OSPF may have told him about a route, but he doesn't really know what's in R2. He's going to make a decision. R1's going to make his foreign decision using his own routing table. Now, just because R1 is okay doesn't mean that R2 is okay. What if R1 is perfectly configured, but R2 has an error in it? This could cause a ping to fail because R1 would deliver my ping echo request reply to R2, but R2 wouldn't have the proper configuration to send it back. So just because, look at that number 3, just because I have routing information about a path to get there doesn't necessarily mean that that router knows how to get back to me. It's all got to be consistent, or what the term we use is converged. When the network is converged, all the routers have appropriate, consistent information in their routing table so that I can ping from any point to any other point, and the connection will be successful. So here's a routing table entry. So the very first thing is the route source. How did he learn about this route source? Well, it has the letter O in there. He learned it via OSPF, which is a dynamic routing protocol. And then here's the actual network that he learned about, and it's subnet mask. So the third entry is, what is the administrative distance? That's, remember the Boy Scout oath, trustworthy, reliable, friendly, all this other stuff? That's like, how reliable is this source of information? So OSPF has a metric of 110. Now, if I use Cisco's EIGRP, that has a administrative distance of 90. That's more reliable. It's the lower number is the better. The metric is the actual metric that the routing protocols come up with. So this is based, with OSPF, it's based upon the bandwidth. And again, we have to take that big bandwidth and we have to sort of put it in the bottom of a fraction and turn it into a smaller number, because the smaller the number, the better. The next hop IP address is how to get to that destination next hop network. Then we have our route timestamp, which means that how long has it been since this route has learned. And then the exit interface is the interface that we're going to pump the copy of that packet out onto to get to the next hop router to get delivered. In IP version 4, it's very similar. We have the O means OSPF. We have the whole network prefix. In this case, it's a 128-bit IP version 6 address instead of a 32-bit IP version 4 address. We have the same administrative distance and metric, and we have the next hop IP address to get there and the exit interface. Very similar, except 128 bits instead of 32 bits. So in order to hear from another router about remote networks, the router has to have an active interface configured with an IP address of subnet mask that's proper, a directly connected network that's connected to another router. So when we look in the routing table, we'll see the directly connected network on this router with a C. That was that serial port in the graphic we saw earlier. The routing table has the prefix and the prefix length. The newer routers also have a sort of duplicate of the C with the L, which is the entire IP address. The C prefix just contains the network prefix itself, doesn't contain the actual host address. The L contains the entire 32-bit or 128-bit address. So after directly connected interfaces are configured, they're automatically added to the routing table. I don't have to do anything. After I configure a dynamic routing table, a dynamic routing process, which we'll do after spring break, those routes, the O's, will appear in the routing table. But what if I want to configure a static route? What if it's a security situation? I don't want to use a dynamic routing protocol because it's giving the farm away. Or what if I am using a dynamic routing protocol like OSPF within my company, but I want to put in a static route, a static default route to my ISP, so I have connectivity so my customers and trading partners and so forth can reach me. So static routing, three uses. In a smaller network, that's not going to change much. It's fairly easy to use. We can use a single default route to represent a path to any other network. And this is used for stub networks. So for example, the South Campus of Tarrant County College is a stub network. It has only one route that goes back to our Trinity River data center. So if anyone wants to talk to anyone on South Campus, they're going to send it to the TCC Trinity River campus, and then it'll send it to South Campus. If anybody at South Campus wants to talk back to any of the other campuses or to anybody on the internet as a whole, there's only one way out. We're going to go through our lease line to Trinity River Data Center, and then it will connect us to the other campuses or to the internet as a whole, whatever we need. So in the routing table, it's going to look like this when we put it in the routing table. Here's the configuration command that actually does this, a sneak preview of what we're going to get in the next chapter. So if it's IP version 4, we're at R1 right here, and I want to add a static route to the 10.0.4 network, which is this network over here back at the home office. And it's not in my routing table because it's not directly connected to me. Okay, there's another router and at least phone line in the way here. So I'm going to put in the command that says IP route, that destination network that I need to get to, which is over here. And what's the subnet mask? And then how do I get there? What is this number? 10.0.3.2? That's this interface right here. That's called the next hop IP address. So I'm directly connected to that lease line that goes to that next hop IP address. And I know if I just forward my information to him, then he will take over, and he's directly connected to that network, the 10.0.3 network, and he'll forward that information to him, that 10.0.4 network. If it's an IP version 6 network, it's the same sort of scheme. I'm going to type IPv6 route and then type in the network, the remote network I need to get access to. This one right here, same network. Just it's dual stack. It's IPv4 and IPv6. And then I'll put in the IP address of the next hop router, the IP version 6 address right here. Easy peasy. Now, if we're using dynamic routing protocols, we're going to crank up a dynamic routing protocol on router R1 and R2. And in this class, we would use something like OSPF. So let's say this represents South Campus, and R2 represents the Trinity River Data Center, which has the connection to our internet service provider. So if I want to connect to the dean at the Trinity River campus, or I want to go to a connection on the internet, I have one single static route configured in my router R1 that will get me back to that internet service provider, and I'll get a connection to it, or back to Trinity River campus. Now we're running a dynamic routing protocol within the entire Tarrant County College network system. Let's exclude the ISP, just our own internal networks. And we're going to use, we actually do use OSPF. We used to use EIGRP, but 10 or 15 years ago, they switched to OSPF. So the dynamic routing protocols automatically discover all the networks. The routers, I call it routing by rumor. The routers gossip with each other, and they tell them about networks they know about. And all the routers get consistent entries in all the routing tables. And we should be able to ping anywhere in any of the college campuses that Tarrant County College is connected to. And we should be able to connect to anywhere on the internet because we have a static default route to our internet service provider. So when we look at the show IP route command on this, we can see they've omitted some of the directly connected networks. R1 knows about the 10.4 network and the 10.5 network because R2 told him about it. R2 knows about the directly connected networks that R1 is connected to because R1 told R2 about it. So in IP version 6, we're going to, some of this is beyond the scope of this CCNA 3 course, switching, routing, and wireless essentials. And in the next 8-week course that we take after spring break, we're going to look at OSPF dynamic routing configuration for both IP version 6 and IP version 4. We'll get to see that in detail, but today it's just static routing. So the default route has been established here at the South Campus. And if I want to go to the internet, like to the Netacad site from the school lab, the default static route will send it to R1, R2 at the Trinity River Data Center, and the Trinity River Data Center will send it to our internet connection, and we'll be connected to the internet. So default route is a special entry that's 0.0.0.0. Let's talk about that number for a second and what it means in IP networking. You guys that have built PCs and Windows PCs, you know about the wildcard. If I type delete star, what files get deleted? Every file gets deleted. Star matches all possible file names. Doesn't matter what the file name and the extension is. If I say delete star, all the files in that folder are deleted. The wildcard in IP networking is all zeros. So 0.0.0.0 for IP version 4 is 32 zeros. That means matches everything. That matches every address. It doesn't have to be 8 bits or 16 bits or 26 bits. 0 or more bits match. It matches all addresses. So that means when I'm at this workstation right here, and I type an address that doesn't exist, have you noticed that all the TCC's internal addresses are 10 dot something? What if it's a Cisco Networking Academy, which is 72 dot something out here on the internet somewhere? Doesn't match. So when it hits my router, that will match that default entry that says IP route 0000. There's no specific entry for Networking Academy on our little internal routers. We would clog them up if we try to put those main entries in there. But that says to the router, send that default entry to the ISP's router, and he will make that connection for us. So IP version 4, they came up with this in the late 70s. He uses a classful addressing ended in 1995. The problem was we started running out of all these class A, B, and C addresses. So IP version 4 table is organized using this classful structure. Then these routes are called child routes and parent routes. So the major network that it came from, say I've taken a 192.168 network and I've subnetted it to the 192.168.1.17 with a /28 subnet mask. Directly connected networks are indented in the routing table, and parent networks are at the beginning of the line. So you can see the major network that this subnetwork that we're using, that we created, what network it came from, and the child route includes the next hop address or the exit interface. So the route it came from is called the parent route, parent routes and child routes. So if we look at this particular chart here, we can see that, oh, look at this entry here. Here's a parent route. It's been subnetted into a subnetted route. Here's another parent route, and here's his children. Here's another parent route, and here's his children. So these child routes, these are indented. You notice that this one is indented and this one is indented. You can tell it's a child route. The parent routes there at the left of the line, they're not indented. They're the major, what we call the major network is the classical network that it came from. So the reason, why did they do this nonsense? Well, the reason is when the router receives a packet, he first of all looks at the parent routes to see if any of them are a match. And if he finds one that's a match, let's say he finds this one's a match. Oh, now I'm going to look through these lines. Fewer lines to look through. He can look at the parent routes. There's only 4 parent routes, and there's a dozen lines in here. And then when he finds the parent routes that matches, he'll just look at the children routes that are in that indentation, and that way you can do the lookup more quickly. It's done purely for programming reasons to make the route lookup process move more quickly. Now, classical addressing doesn't exist in IP version 6. So IP version 6, they're all essentially parent routes. The administrative distance. What if I used more than one dynamic routing protocol on a router? That's not common practice at all. But say maybe my company's running OSPF and I bought another small company and they're running EIGRP. And until I get their network completely reconfigured, I'm going to have to run 2 routing protocols in the junction between the company we bought and our company, until I get things all straightened out and unified. So it may be possible for some routers to run EIGRP and OSPF at the same time. So which routes get installed on the routing table? The OSPF routes or the EIGRP routes? The administrative distance is the tiebreaker. This is the trustworthiness. So EIGRP has an administrative distance of 90, and OSPF has an administrative distance of 110. EIGRP is a Cisco proprietary route, so they have written the code to make it more trustworthy. He would use that as the more trustworthy route. So here are some various. OSPF is the only one we're going to use. We used to use RIP. We used to also use RIP, and we also used to use ISIS. We also used to use EIGRP. But on a going forward basis, as Dilbert says, thank you to the pointy-haired boss for reeling out time travel. On a going forward basis, we're only going to use OSPF. And everything, any other routing protocol we discuss will be just for theory. But we're not going to have to learn the code for it. Okay, when would we use static routing and when would we use dynamic routing? Again, I'm going to give you the big picture one more time. We are definitely going to use dynamic routing within our company to get interconnectivity between all our campuses, using, for example, OSPF. We're definitely going to use one static route to point to our internet service provider, because we don't want the million routes present on the backbone of the internet to clog up our little bitty $1,000 routers that we use for branch office routers. You need $1 million router to do that. So static routes, he says, are commonly used as a default route. Yes, that's the most important common use of a static route, as a default route back to a service provider. Dynamic routing protocols are commonly used in, well, everywhere. Networks consisting of more than just a few routers. Yes, we don't want to start a bunch of static routes and have to change them all the time. Networks tend to change. Corporations move and change and grow things. So in any type of company, we're going to choose a dynamic routing protocol. OSPF would be okay. You might want to use EIGRP. We learned that at the CCNP level, but at CCNA, we're just looking at OSPF. That's the way this works. The advantage is if there's any change in the network topology, the network will automatically find the best path. If there's any growing in the network, the dynamic routing protocol automatically learns about any new networks. You don't have to run around to 100 routers and reconfigure static routes. Everybody uses dynamic routing within the company equipment that they have control over, and then they point with a single static default route to their service provider that gives them connections to the internet. So if we look at a comparison here, dynamic routing is independent of the size. It can grow. It's going to work okay. If we use static routing, it's going to be much more cumbersome with a bigger network. Dynamic routing automatically adapts to changes. Static routing, oh no, I got to run around 100 routers and change them all because the engineering lab added one new switch. Scalability, which means that I can ramp up the network and add capacity to it. Dynamic routing protocols automatically adjust for this. Static routing, only suitable for small, simple topologies. Now, here's a downside for dynamic routing. Security must be configured carefully, because dynamic routing protocols are like telling everybody else about the network. If I use a static routing protocol, this is the one big advantage in a large network of a static routing protocol. Security is built in. There's no OSPF hello packets telling everybody else about the rest of the network. Nothing is sent between the routers. Now, another advantage of static routing is that it doesn't consume extra CPU, memory, bandwidth on the links to send all these updates back and forth. In a dynamic routing protocol, yes, we do need some CPU cycles, we do need some memory, and we do need a little bit of bandwidth on the links between the routers to send the information back and forth. Now, static routing, I say what the path is exactly. With a dynamic routing protocol, the rules that are built into the dynamic routing protocol are going to choose the best path. For example, OSPF will try to choose the paths with the fastest bandwidth. So over the years, we've had some routing protocols that were commonly in use. RIP version 1 and RIP version 2 were very commonly in use until about the end of the 90s. OSPF has came along. Cisco came up with their EIGRP to compete with RIP. And so with the advent of IP version 6 in the late 90s, all of these routing protocols have an IP version 6 version as well. So if you want to run an IP version 4 and IP version 6 dual stack network in your company, you can use OSPF, you can use RIP, you can use EIGRP, whichever one you want to use. Routing protocols are defined and organized as to whether they're interior gateway protocol that we would use within the junior college network, for example, or within your company, or an exterior gateway protocol that internet service providers would use between each other. So distance vector routing protocols like the ORIP version 2, IGRP and EIGRP, they're called distance vector routing protocols because they send the direction and the number of hops to the destination network. Link state routing protocols like OSPF, all the routers have it's like the difference between going to a gas station and asking how to get to the next town. That's a distance vector routing protocol. Having a MAPSCO or a GPS, that's a link state. I've got the complete exact topology of the map of the road, and I can choose the best path and maybe avoid a road because it's telling me there's a traffic backup on that. Exterior protocols are used between ISPs. So border gateway protocol is the one that you use here. And you will never have to use that in a company if you only have one connection to an ISP. But if you have a connection to 2 ISPs for redundancy, you might need to configure border gateway protocol. Not a CCNA topic, that's a CCNP topic. So dynamic routing protocols discover remote networks, they maintain up-to-date information, they choose the best path, and if the best path that was the best path becomes unavailable, they'll try to find a new best path. It might be slower, but it's the best way to get there now because the main path is not working properly. And when we look after spring break, we're going to see they do this by sending out hello packets to each other to discover the network. So all dynamic routing protocols use a table or database in the RAM memory of the router. Doesn't matter whether it's EIGRP or RIP or OSPF. We're going to talk about OSPF later on. So OSPF keeps a table or database of all the links he knows about to get to the networks. Routing protocol messages are used so that OSPF router R1 can discover another OSPF router R2 and start exchanging information with them. An algorithm, thank you, Al Gore, for inventing the internet. An algorithm is like a flowchart or a list of code steps to take to accomplish something. So routing protocols will use algorithms for determining the best path. For example, OSPF has an algorithm that says, choose the one link that has the fastest bandwidth and use that one. The best path is determined by something called the metric. The metric is a number that we have to reduce to a low number is the best choice. So if the big football game was coming up and we had 2 halfbacks running and the coaches have both run the 50-yard dash, and whichever one is the fastest runner gets to start the game. So one of them runs it in 7.5 seconds and one of them runs it in 7.3 seconds. Who gets to start the game? Well, the guy that ran it in 7.3 seconds is the faster runner. He had the best metric. The lower number is better. It's a faster runner. So a metric is a value that's used, that we use to measure networks to see which ones are faster, for example. Now, the old RIP, Routing Information Protocol, the metric was how many hops, how many routers between us. And his theory was, if I have one path that has 5 routers along the way, another path that has 3 routers along the way, the 3 router path is the most optimum path. I would use it. Doesn't matter what the speeds are. RIP can't measure speed. Open the shortest path first. The metric is cost, which is bandwidth, cumulative bandwidth. It's kind of like the cumulative bandwidth with STP to figure the best cost back to the root bridge. We're going to use the fastest path back to the root bridge. So OSPF routers will use the fastest path back to another destination. EIGRP is kind of like OSPF. It uses the speeds of the lines, but it uses some other things as well. But we don't have to worry about configuring that at this point anymore. If there are 2 or more ways to get to the destination and they're equal, let's say I have 2 10 gig fiber optic cables to another router. And since they're both exact equal cost, that is the same speed, I can distribute equally among the 2 of them, and I get a total of 20 gig. It's called equal cost load balancing. And it's done automatically by the dynamic routing protocols. And if I do it with, I can do it with static routes if I want to. Now, EIGRP has a weird ability that if they're not exactly the same speed, say I've got a 10 gig fiber optic line and a 1 gig copper line, I can unequal load cost balance across them. I'll put 90% of the traffic on the fiber and 10% of the traffic on the copper cable. EIGRP is the only one that can do that. But we won't have to learn how to do that because we no longer have to configure that. Okay, now hang on just a second, and I'll pull up the next one, and we'll start with static routing. Okay, so these are different types of static routes we're going to look at. Commonly implemented in smaller networks or where you want high security. Typically, you are going to be running a dynamic routing protocol like OSPF within your corporation or company, and you're going to figure a default static route back to the home office or a default static route back to your internet service provider so you can get connection to the internet, but you don't want thousands of entries in your routing table to slow them down. So static routes, you can configure them for IPv4, IPv6. We saw the command IP route, IPv6 route in the last slide, last set of slides. So they both support these 4 different types of routes. So let's look at what these things are. When I can configure a static route, I can identify where to send the traffic to. I'm going to specify a route and say how to get there. I'm going to either say, what's the next hop IP address to get there? Or I can say, what router exit interface do I want to go out to? I want to go out to my G00 port. I want to go to my S1/1 port. Or I can specify both. I can do a fully specified static route and it's specified both the next hop IP address and the exit interface. And this is sometimes required with Ethernet connections because Ethernet is a broadcast multi-access network. If I tell it to send it out the Ethernet port, it's going to go, well, to who? To what MAC address? I need to tell it the next hop IP address so he can send it to that next specific router. So here's the syntax for this. We're going to go to the global configuration mode. Be in the global configuration mode, type the command IP route, and then specify the network and its subnet mask, and then one or two of these 3 possible ways. What's the next hop IP address? What's the exit interface? Or what's both of them? And we haven't talked about this yet. I can do the administrative, something like kind of the administrative distance, and create something called a floating static route that will drop into, when the main route fails, it'll drop in and take over. In the IP version 6 world, it's almost the exact same syntax. I'm going to specify the command IPv6 route, then specify the network, and then prefix number like /64 is very common, and then how to get there. Now, in a dual stack refers to when a company is running both IP version 4 and IP version 6 at the same time. IP version 4 is old, it's deprecated, we should move away from it as quickly as possible and migrate over to IP version 6. But there's a lot of equipment that's still configured to be IP version 4 and it's going to hang around for a long time. So let's just run both protocols at the same time. And many ISPs are offering this now. If I want to go to the IP version 4 address of someone on the internet, I can go to there. If I want to go to the IP version 6 address of somebody on the internet, I can go to there or within my internal corporate network structure. So right now we have this topology set up, and there are no static routes are configured, which means that R1 can only connect to his directly connected devices. R2 can only connect to his directly connected devices. R3 can only connect to his directly connected devices. PC3 cannot ping PC2 or PC1. There is no static route that's been established yet. So when we look at the routing table, he's typed the command show IP route, and he sees the directly connected routes on R1. Now he can ping his own device, but if he tries to ping another network, it's not his directly connected network, the ping fails because he doesn't know how to get there. There's no static entry in the routing table yet for him to do this. Similarly, with IP version 6, he has direct connection to his directly connected IPv6 networks. His addresses on his network, R1's network, succeed. When he tries to get to one of the R2 or R3's host machines, they fail. Can't be connected. So let's configure some of these routes. Let's go to R1, and you remember that diagram, there were several other networks he didn't know about yet. So we're going to configure the 2 network, and we're going to configure R1 and tell them how to get to the 172.16.1 network and the 192.168.1 network and the 192.168.2 network. And we're going to type these 3 lines of code into R1, and now he knows how to get to the other networks. Now they don't know how to get back to him yet. Remember the Zen, we have not yet configured R2 and R3 to have consistent information in them yet. So this is a job that has to be done on all 3 of the routers that's consistent with all the other routers. IP version 6, it's a similar type of thing. We're going to tell the router R1 how to get to this network and this network and this network. And then once we've configured the return paths in the other 2 routers, we'll be able to ping those devices we were not able to ping before. Now, when configuring a static route, I can use the exit interface to specify the next hop IP address. So if I'm using serial ports, for example, I can specify the network, the remote network I'm trying to be able to reach in the submit mask, and then say, pump this request out the serial 0/1/0 port to get there. Directly connected routes only work well with a point-to-point serial interface, because with point-to-point serial interfaces, it's not a multi-access network like Ethernet. There's no ambiguity. So we could do this with IP version 6 in the same fashion. We could specify the exit interface, S0, 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 and get the connectivity. Now let's remember what a fully specified route was. That's one where I both specify the next hop IP address and the exit interface. I have to do this with Ethernet. So in this case, we have an Ethernet-based network. So I'm going to specify these 3 remote networks I'm trying to be able to get connectivity to, and I'm going to say, go ahead and send that information out the gigabit 001 port, but to which other device? I have to put the actual next hop IP address of the other device for it to be connected there. So it is recommended that when the exit interface is an Ethernet network, that the static route includes the next hop address as well as the Ethernet port for best connectivity. With IP version 6, if we try to specify the next hop IP address, he says, oh, that's too ambiguous, it's Ethernet. Let's specify the exit interface and the next hop IP address as well. So he specified the full one here, and so it shows up as the static entry in the routing table. Here's the remote network we're trying to get connected to. 1 hop away. There's the next hop IP address, and there's the exit interface. It's been fully specified, and after we go to R2 and R3 and put the corresponding matching consistent entries in them, then we'll be able to ping back and forth just fine. So let's verify a static route. We can type show IP route static, and that's like show IP route, except it'll just show the S entries. We can type show IP route network and just show specific networks. And we can do show running configuration and look at all the commands that start with IP route or IPv6 if you want to do IPv6 and look at both your IP standard version 4, it's just IP, anything IPv6 is, you stay IPv6. Now, we're going to use a dynamic routing protocol almost all the time within our company network. but we do need to configure a default static route to get back to the home office or to our internet service provider. So a default static route is a route that matches all packets. We're going to use that address as 0.0.0.0, which matches, it's the wildcard, it's like the star.star in DOS. It's going to match everything. Now, if there's a more specific entry in the routing table for PC1, that will match, and it will use that route to send out the G00 port, and PC1 will get it. But if it's not a route that's in our internal company network, let's say everybody on the network is 172.16. something. Maybe it's an entry on the internet, like 72. something for the network academy site. That won't match any of our specific internal addresses. No bits match. It'll be sent to the home office or to our internet service provider, and he will give us a connection. And when you look at the show IP route command, this has showed up as the gateway of last resort. So IPv4 default static routes, the syntax is as follows. We're going to say IP route 0.0.0.0, which is any IP address, any subnet mask. And then we have our choice of either the next hop IP address or the exit interface or both. Same thing with IP version 6. We're going to specify IPv6 route. And in IP version 6, instead of typing out 132 zeros, we use the colon. Remember that in IP version 6, when there's a bunch of zeros, you can represent them by a double colon. So this double colon part means it's 128-bit 0 any address. And the /0 means subnet mask /0, 132 zeros. Matches any IPv6 address. That's not more specifically matched in the routing table. And then we put the IPv6 address in the exit interface to get connected to it. Okay, so let's configure a default static route for R1. We're going to go to the global configuration mode, say IP route quad 0, and the next hop IP address to get to that location. IPv6, same thing, IP route. Here's our 128 zeros times 2, and there's the IPv6 address, the next hop address to get to that router R2. We can verify this. We can show IP route, and we will always see when the default route has been established, we'll say gateway of last resort has been set to this network. And then we'll see an S* entry in there. This is the default static route. The default static route is the route that points to our ISP or our home office. A regular old static route, like just to get to one in the network, won't have a star. But the default static route always has the asterisk character in there. So normally in most companies, we're going to see some O's for our dynamic routing, and then we'll see one S* at every router to get back to the home office. So we can verify this by typing show IPv6 route static. In the case we see our IPv6. Now there's a peculiarity in the Cisco iOS that there's no star for IPv6. It's just a regular static route. But you can tell it's a default static route because it's all zeros. I think they're trying to confuse the students. Now let's talk about floating static routes. Let's say I have a dynamic route or a primary static route, and I have a backup route that I want to use if the primary route goes down. So I can configure a floating static route with a higher administrative distance than the primary route. For example, if I'm using OSPF and my primary route is the OSPF, well, the administrative distance is 110. And what if the OSPF process fails? I can put in a floating static route with an administrative distance of 120. If the OSPF route fails, all of a sudden the 120 is now the most desirable route, and it will be installed on the routing table. Now, by default, they have an administrative distance of 1. It would overrule them. So we have to not accept the default of 1 and put a 120 in there. That way it floats above the other more preferred route, but with the more preferred route fails, it'll take over and give us some fault redundancy, some fault tolerance, so that we can still continue our operations. So I could do this by, in this case, I could configure a default route to this IP address and don't put a number. And by default, it's 1, the most desirable metric. And I could put a floating static route with the number 5. The number 5 route will only be used if the number 1 route fails. And then he does a similar thing for IP version 6. Then we could test this. We could shut down the interface that it's supposed to use. R2 shuts down both the serial interfaces, and then we could start using the secondary route because the primary route would vanish from the routing table when he's no longer available. Okay, a host route is a special 32-bit mask which simulates an individual host machine. We're going to use some loopback ports in the lab that we're going to do on Thursday. I could attach real PCs to real Ethernet ports and configure them with IP addresses, but for testing purposes, to just have a number to ping, I can set up a loopback port and configure it as a host route, and that way I can say the actual 32-bit address. Now, in the newer Cisco routers, when you have that C entry, that's the network address. The L, the link local, it's kind of like a link local, that's the exact entire 32-bit address. We'll see more about this in a later course. So whenever I configure an interface address on a router, he installs the C for the network portion and the L for the entire host address itself. So you can actually look in the show IP route and see the IP addresses of your individual devices. Or you could show IP interface brief for show interfaces to see it, but you can actually see it in the routing table now. You couldn't see that in the earlier versions. So static host routes would send something to a particular device. In this case, we're using a static address of 209.165 to simulate a particular host machine or server machine used in the lab. Sometimes I'll do this in the labs. Instead of configuring a PCA, you'll just configure a loopback port on the ISP to simulate that server address. You can't log into the web server on it, but you can ping it and test connectivity to it. So to configure a static host route, I'm going to configure IP route. Here's our route. Here's our subnet mask, and that's a /32, all 255s, and there's the next hop address to get there. And you could do the same thing with IP version 6. To verify these routes, we're going to do show IP route, and here's our route that we put in there with the IP version 6. Here's the IP version 6 corresponding address for that, and the next hop address to get to it. Now we can configure IP version 6 static host routes with a link local address. Now the link local address, this is a globally unique IP address for IP version 6. Okay, this is a link local address. It's only used within the network, and it's typically used between routers and switches, so I don't have to use a global unique address. FE80 is the prefix for the link local address. So maybe the first router would be FE80::1, and the second router might be FE80::2. And we could connect our devices together because the routing protocols like OSPF would rather use the link local addresses to send the hello packets back and forth to each other and to do the routing table updates. We'll see more about that in the first chapter of the next. Okay, now let me stop at this and go to just a few slides left here, and we're going to be all done and do the troubleshooting. Now, let's look at packet forwarding. PC1 addresses a packet, and he wants it to go to PC3. He sends it to his default gateway. Right here it is. It's the envelope of the default packet. When the packet arrives at the R1 gigabit 000 port, R1 is going to de-encapsulate the Ethernet frame, pull out the packet, and look in this routing table for a matching network entry. If R1's address matches a static route entry, remember, put a static route in R1, we never see the code for R2 and R3, assume they're properly configured though. He'll use the static route to identify the next IP address, and he'll say, set it up here. If it doesn't match it, it'll use the default static route. If we haven't configured any kind of regular static route or default static route, since the destination address of PC3 is 192.168.2 and router R1 doesn't know about any of those addresses, he would drop it. And he would send back, as a courtesy, he would send back an internet control message protocol message back to the source saying that, sorry, I tried to deliver your message, but I didn't have a route for it. Now, assuming R1 had an entry that matched, it's going to encapsulate that packet into a new frame and send it out to the router R2. R2 is going to look at that, unencapsulate the packet, look in this routing table, assuming he's consistent, the network's converged, everybody has connectivity, he'll send it here. Then finally, it'll reach router R3, and R3 will send it to his workstation. He'll be able to receive it. And when R3 receives it, he'll send back the reply to the ping, echo request, echo reply, and PC1 will get the reply back from this ping showing that it was processed properly. Now let's look at troubleshooting IP version 4 static default route configuration. Why can networks fail? Well, what about an interface fails or someone accidentally types shutdown on it? What if a service provider connection goes down? Maybe the phone line went down. What if the link is so busy that it's just dropping traffic right now? Oh, what if you've entered the wrong configuration? Oh yeah, well, you know, learning networking is like, it's like karate. In karate, you got to do 10,000 falls. In Cisco, you got to do 10,000 configs. You're going to make some mistakes. So network administrators should be able to figure out what's wrong and solve the problem. Now here I have a concept of something called problem ownership. If it's within our company, we get to fix it because it's our job. If it's out of our company, we can't fix it. It's someone else's job. We can try to notify them or call their help desk. So we need to be able to isolate the problem and determine, is it within my company? Then I need to get on it right fast. If it's outside my company, try to notify that, you know, Google or whoever what the problem is. So ping. End-to-end connectivity. We do have some extended pings that can do things like more than just the default 5 pings or make the packet bigger. Verifies network layer 3 connectivity to the destination as a either succeeds or fails as a whole. What if it fails? I don't know where. Traceroute will show me there's 10 or 15 routers between me and that destination network. If there's a failure, it'll tell me where the failure has occurred between router 5 and router 6. Well, are router 5 and router 6 our problem? Or is it some other company's problem? Then I need to know whether I need to fix it or not. Problem ownership. I can type show IP route and display the routing table. If the destination network is not in the routing table and there's not a consistent default static route, then there's a problem with that router. Show IP interface brief will show me that the network addresses on my router are proper and if either up and up. If I forgot to type shutdown or mistype a common mistake is instead of typing 192.168, you fat finger, you type 129.168. It's very difficult to see with your eyes. Your eyes, you will actually literally hallucinate yourself into not seeing the 129 and seeing the 192. And you ask your neighbor to look at the lab. He says, you dummy, you fat fingered it. Now, you guys know this is my favorite, show CDP neighbors. Before I ever proceed with doing any lab, I like to bring up all the wires, plug all the devices together. If it's a router, do the no shutdown, no IP address is required because Cisco Discovery Protocol is layer 2 data link layer only. And show CDP neighbors, give host names to the R1, R2, S1, S2, and make sure they're all connected together properly. You know in that lab you're going to do on Thursday, you got R1, R2, S1, S2. It would be wise before you proceed with the lab to show CDP neighbors and make sure the wires are properly done, particularly since you don't get to touch the wires, I have to do it for you. Make sure that all marked didn't make a mistake and tie them together incorrectly before you get started and waste a bunch of time. So let's look at a connectivity problem. Connectivity from PC1 to PC3 failed. Extended pings fail. Now, pings from R1 to R2 are good. Pings from R1 to R3 are good. R2 routing table, the problem is in the R2 routing table. It lacks a static route. It needs to have connectivity. So this is one of the things why static routes, even in simple networks, can be kind of difficult to configure properly. Okay, so that covers all 3 modules, and I'm going to hang loose. Hold on a second, let me stop recording.